Well, so
Evidence.
try to switch places with the other presenter, but apparently.
He's even more today than you.
Sorry. Well, I'm going to talk about subject that has some practical relevance. It's related to what we do with information is that on small scales, cosmology, where our models are not sufficiently evident. And this is related to a work recently submitted with these collaborators, particularly Roger. I'm assuming you know, my advisor for passage. So the issue is we can get a good deal of cosmological information from the large-scale structure of the universe. We can calculate how perturbations evolve through cosmological perturbation theory. Then we can compare these predictions with observables. The main observables for large-scale structure are galaxy counts, mostly 2-point correlations. And from this information, we can constrain cosmological models and get information on, for example, the sum of the genome masses or the model. But a key point is that in the end, we need to connect predictions on matter perturbations to galaxy correlations, which is what we observe directly. So I'm going to talk about this last link in this chain that starts with the assumption of a cosmological model from which we can compute matter perturbations. Then we can predict what the galaxy correlations are. And this is done currently through the mechanism of the galaxy bias expansion. This allows us to connect galaxy fluctuations to matter fluctuations. So one problem that we face is that this expansion takes both 4 or 5 free parameters, which are nuisance parameters. And that tends to make the analysis more complex. The parameter space rises in dimension. It has later a complicated geometry. It causes volume projection effects. So one approach that is used, for example, in the dark energy survey is to truncate the expansion to just the first term. And this gives us the linear bias model, which is simply a statement that the galaxy fluctuations are proportional to the matter fluctuations. And this is true down to K approximately 1.1 inch per megaparsec. This is approximately this of the order of magnitude of the average distance between galaxies. Yes, well.
Just a very silly question. So you say that the linear bias fail at 0.1, which is actually pretty large scales. How do you know that this linear bias fails around there?
It depends on how many free parameters you have in your estimations. If you have many free parameters, cosmological parameters, then we can tweak things and push this towards 0.3 megaparsec. But here I'm assuming everything else is almost fixed, and you adjust only this linear bias parameter, E1, to fit the observations. Then that's mostly 0.3.
And you
That's
have
when
simulation.
Then that's when you have a tension in cosmological parameters that's about 1 sigma, maybe 0.5 sigma. Okay. So this is the solution. This is the situation that we have. We have a prediction which involves some relative error. And this is you can see the error bars. If we push the analysis to very
Sorry,
small,
Alex. Explain, what is this graph is plotting? This is the CL, the galaxy-galaxy correlation is what?
yes, this is the related error on galaxy clustering. I'm gonna specify what these data vectors are later. Here, I want to show that our model fits the observable down to a certain scale. Here it's corresponding to three-dimensional momentum variables to about 0.5%. So it fits well within the experimental error. However, if we decide to push this beyond this scale, then we have a large tension, and this will bias the analysis. So we have to perform what's called the scale cut. We describe scales that go beyond the regime of validity of the model. So this is for galaxy bias, but it's a general problem when we try to fit cosmological models to small scales. For example, there is the issue of ionic feedback. It has been studied by one of our students, Gabriela Moreira. And she used the same analysis, the same model that I'm going. I applied here to the case of bias. So this is an alternative that we can explore. We can restrict the analysis to linear bias, but we have some information on higher order corrections that we don't include in our model, but we treat as theoretical error. And we treat this error as a random variable. And we include this inserted in the analysis, we marginalize over it. So it's included in the covariance matrix that we use to analyze the data. So what happens is that we add theoretical error and we enlarge the error bars. And then we can accommodate the observables towards smaller scales.
So this theoretical error is just variable in the feedback or also nonlinearities or?
We can do it for all these effects that appear on small scales. But here I'm restricting the analysis to linear bias, to galaxy bias. So the error counts on nonlinear galaxy bias to 3 or 4 operators that appear in the expansion that we like on. So we enlarge the error bars, so the statistical weight of these data points is reduced automatically. So if this works well, we don't need to concern ourselves with the choice of K-max, because these modes are suppressed automatically, and they won't influence the analysis, they won't bias the analysis. And there is another benefit that we can expect to get from this, which is we are using smaller scales, and we can get some information from them, even if their weight is reduced by theoretical certainty. And this would improve the constraints on cosmological parameters. Yes.
When you're talking about theoretical error, so these systematics, it's just a guess that you won't bias the result, because you might increase the error bar, but still be biased because your theory might be biased itself, right? So it is a good guess, but it's still a guess. I mean, you're minimizing the impact of a bias in your theory, but you're not eliminating it. It's just making it less of a concern, but the bias might be there. It's not like you're eliminating.
The
You cannot
bias might
eliminate
be
that.
there, and this is a tentative problem. If I reduce this error bar by, let's say, 5%,
But you're not
50%,
eliminating
let's say.
bias, you're just mitigating that possible bias, because you don't know what it is. It's not eliminating bias, you can't know that.
yeah. So we must be very careful about how we model theoretical error. So let's suppose I reduce this error bar by 50%. Meaning I underestimate the theoretical certainty. Then I include these small scale modes with large statistical weight, and that will bias analysis. There's also a possibility that I overestimate theoretical certainty. And this, well, erases the benefit that I would have by including these small scale modes. And it could even increase the uncertainty with respect to the scale, because as you see, there is some uncertainty on all steps. So it's good that you ask this question because it anticipates that this model, this mitigation model is sensitive to how we model the theoretical error. So we must be careful on this. So this is the expected result. Here you see an estimation with theoretical error that we did with very large K, K max equal 1, so 10 times the original maximum scale. But the small scale modes have not affected the analysis because they have been suppressed. And we have a small gain in precision with respect to a scale cut at 0.1, which is shown in red. We also make for comparison a naive analysis with a scale cut at 0.5, wholly inadequate. And you can see, well, first we have a very poor fit, and we have a strong bias in the results. So the inclusion of theoretical error brings this best fit to closer to the fiduciary value.
Correct, yes.
Yes?
So just a silly question then. How are you computing the error without the theoretical error?
That's a scale cut. I'm just fitting the linear bias parameter.
Right.
With these two cosmological parameters, omega C and sigma 8.
Right, so the theoretical error bars in that plot are coming from linear theory then.
Oh, okay. Well, these error bars that you see.
No, the error bars in the other plot. Like the gray line, the red lines, yes.
Okay.
How do you obtain it?
Okay. This is a plot by Paulo from
Okay.
a few years ago. It shows very well the situation I'm trying to describe.
Mhm.
If you, this darker gray result shows the analysis without the theoretical error. What happens is that when you push the analysis to small scales, we get a good deal of precision, but we bias the result above the fiduciary value. When we include the theoretical uncertainty, then this gets accommodated. These small scales don't hold the analysis, and we get something close to fiduciary value, which is the same that we see here. Okay. So let's talk about this galaxy bias expansion. So as I said, we assume a cosmological model. We deduce from it what's the evolution of matter variations, and then we get galaxy configuration. So in the last chain of this analysis, we must relate matter fluctuations to galaxy fluctuations. And this is the so-called bias expansion at second order. So it comes from assuming that galaxy formation is a local process. It's you can imagine a galaxy as a particle that is free falling. So the way it feels gravity is not by the first order, the first derivative of the Newtonian potential, because it is free falling, but through the second derivatives. It is at most influenced by the gravitational environment at the level of second derivatives of potential. So we simply say that we calculate all these scalar operators that we can construct from this answer and up to a given order. And we express the galaxy fluctuation as a sum over these operators with some free parameters. If we do this well, then we include only the necessary operators, the minimum amount of nuisance parameters in the analysis. So to second order, we have these 4 bias parameters. Then we have to relate this to observables. So the most common observable in galaxy surveys is the 2-point correlation function. In Fourier space, this is the power spectrum. So it's the correlator in Fourier space of the galaxy or matter fluctuations at two different modes. And this is the Fourier transform of the correlation function that you can see by through galaxy counts. But what we actually use in photometric analysis is the corresponding of this in the sphere, celestial sphere, so angular correlations. But it's a simple method to project this prediction to obtain the so-called angular power spectrum. So CG and CG kappa, which is going to be what we will use as data vectors in this topic. So as you saw, there are three parameters. You see how they can cause theoretical uncertainty. If we don't know what these parameters are, then there is a large possibility of error. And they are 4 parameters, there are 3 per redshift beam. So if you have an analysis of 5 or 10 redshift beams, then this scales up. So here I'm just restating what the goals are. We're gonna restrict the analysis to 1 parameter, and then the error that comes from the others, we're going to model as a random variable and include it. And if we do this well, then we don't bias the analysis, and we may get some precision, some improvement in the constraints of cosmological parameters. So how do we do this? We start with the likelihood function. As you know, this is the probability of getting the data given a theoretical prediction. We are actually interested in, when you do cosmological inference, in the probability of getting the model given the data, but this is done through this simple identity. 2 ways in which you can express the probability of 2 random variables. So we get the probability of theory given data in terms of the likelihood and the so-called prior probability. So now let's suppose we have theoretical error. So we have this likelihood that we know of data given theory, but suppose the theory has theoretical error, which we treat as a random variable. So it's the likelihood of data given a theory, a prediction from a simpler model, which is going to be the linear bias angle spectrum, and the theoretical error. So quite simply, it's expressed in this way. But now we assume we don't know exactly what the error is. We don't want to include it in the model, but we treat it as a random variable. And we marginalize over it because we don't care what the particular value of this error is. So if we assume both of these likelihoods are Gaussian, then the result is simply this one. So there is a likelihood of data given the prediction of a simple model, and the effect of theoretical uncertainty is the enlargement of the covariance matrix, which now has the original component given to data, and the covariance matrix of the error itself. And this causes the effect of enlarging the error bars that I described earlier. So now, as it applies to this work, the theoretical error of the simple model is the linear bias angular power spectrum. The fuller theoretical prediction is the spectrum with full bias. There's also the data vector, which we assume contains higher order bias. And the error arises from neglecting these higher order operators. So now we have already assumed the probability is Gaussian, and we want to model covariance matrix in the mean error vector to construct this modified line. So how could we proceed? We can have from cosmological simulations that take account of galaxy evolution, some knowledge on the statistics of bias parameters. We could use this to deduce the statistics of theoretical error due to bias. So the idea is that from the statistics of bias parameters, we could construct an ensemble of full bias spectrum. Each choice of parameters corresponds to one spectrum. So this creates an ensemble of bias spectrum. For each element in this ensemble, we fit a linear bias model, so we have one element of theoretical error. So this creates an ensemble of theoretical errors. And this gives the covariance of theoretical error. But it doesn't work very well. And the point is that we need detailed knowledge of these statistics to reproduce the error reliably. And you can see it in this way. So this is, as I said, the galaxy fluctuation depend on these parameters to linear order. The power spectrum is a product of fluctuations. So we have the prediction of the Fuller theory depends on products of bias parameters weighted by these components that correspond to the meta operators that appear in the expansion. So if I try to calculate the correlator of two fully biased spectrum, I will need to have at least the correlators of bias parameters. And this is a level of information that we don't usually get from cosmological simulations. We have in general the mean value of a parameter and its variance. We don't usually have these higher order correlations. So it's not easy to reproduce from this information in power spectrum, so we can create an ensemble of fully biased spectrum. And the approach that I proposed doesn't work very well.
So I'm just sorry, I, J, M, N here are redshift slices. They are what?
Sorry.
I, J, the indices I, J, M, N.
Okay.
What are you thinking for?
So IJ represent these indices. They denote the operator in the expression.
Oh, you are saying for a fixed redshift bin, then I'm looking at the different bias terms. Okay, so
Yes.
these are the ones. Okay.
Yeah. So
Okay.
imagine in this correlator,
I understand.
understand? Okay. Just to make it clear, in this correlator, there are big products. So there is cross products of each of these terms, and this is the BIBJ that you see in your expression. Okay. So as I said, it's not usual to have this level of detail from cosmological simulations, but we can have mean values and variances. So we won't do exactly the proposal that I presented, but we'll do something that is a compromise between a pure guess on what the theoretical error is and measuring it reliably from simulations. So what we do is we estimate the mean error and diagonal. So let's say the standard deviation of the theoretical error from this data. But for non-diagonal elements of the covariance, that is cross correlations, we are going to use some ansatz. We will assume some correlation length and we'll try to guess it from physical realms. Then we test these assumptions in mock likelihood analysis. So if we retrieve a bias cosmology, we can say the method is successful. We also compare it with the scale cut to see if there is any gain decision. So we start by writing the covariance matrix in this way. There is a diagonal that we call the envelope. because it gives the size of the theoretical error. And correlation coefficients. For the correlation coefficients, as I said, we need to adopt an SS because we can't measure it from the data. So it starts from the idea that the error on similar scales is also similar. So the error is correlated across some coherence length, delta L. And you just choose a function that is well behaved that has this property. So it's the Gaussian function. Our motivation for this is that it has been tested for other cases. For example, for bionic feedback, it has worked. So we want to know if it works for galaxy bias as well. So this is the result of simulations. We can simulate the formation of galaxies in the universe, and in the end, can fit a bias model to it. So we can measure how parameter B2 is related to B1, B double squared to B1. We have they're clearly related, but it has some scale. So we have knowledge of the best fit values and the variance. And we use this to construct the matrix. So we sample over these parameters. This gives the envelope. But as I said, the envelope itself is not exact. So we test two possibilities. One is simply saying that the envelope is the standard deviation of the ensemble that we construct. And the other is approximately 2 standard deviations, which is more or less the 95th percentile of absolute errors. So this is what we see. So this is theoretical error that we see in this way. It's very small on large scales because the linear model works very well. But then it grows as higher order bytes begin to contribute.
So one question here. So what you're obtaining, like the origin of these constraints of the errors is these coevolution relations measured in Illustris or Las Damas simulations.
Yeah.
Would that depend on what's the set of hydro or baryon physics that you are implementing? Because then you could have a different kind of error, a more tight constraint or loosely.
Yeah.
So I may imagine that if you now go to another set of hydro simulations, this might be not sufficiently covering the error or
We
yes.
cannot rely on the measurement of a single simulation. We have to have an ensemble of bias parameters. To have statistics of bias parameters, we need to have a range of parameters that enter these simulations. So as you see here, each gray circle denotes one simulation.
From Illustris.
Yes.
So that's
There is a range. And here this is for Las Damas. Well, you can ask, is there a disagreement between Illustris CNG and Las Damas? Actually, Las Damas produces B2 as well, and BS2. We were able to compare both and they agreed. So that wasn't an issue here. But this one doesn't produce binaural, so we had to supplement it with Las Damas. Okay. So for this coherence length, the approach that has been tried before for this method is choose a coherence length that is more or less the typical scale variations of the spectrum. So if we are dealing with three-dimensional power spectrum, matter power spectrum, then that would be more or less the VEO scales. So one choice that has been made is to choose delta K so that it's larger than the VEO scale, so the error would be correlated at the scales. The simplest choice would be to say that the matrix is diagonal, so delta K is 0. But that's being independent. If we change the meaning, we change the strength of theoretical error. And it treats error at different modes that's completely independent, so that's prompt to increase precision. And we are going to push the analysis to very high Kmax. So this can introduce full use precision analysis. We test these two possibilities and we add another one, which minimizes the signal to noise ratio of the matrix. So it gives the minimum possible precision that we could get from a choice of delta K. And this choice of, this is a conservative choice from the goal of minimizing the possibility of spurious precision being introduced in the analysis. So to summarize our model, we have an envelope that is constructed from this data, simulation data. We have two possibilities, one standard deviation or two. The mean error has been measured from this same ensemble, and we test a few values of coherence. So now we test these assumptions by means of log likelihood analysis.
So, yes, so you could have very well done, included all of these parameters for each redshift in those 4 parameters, right? And you could have fitted for the parameters and then marginalize after that, right? So what you're doing is that you are separating the problem, you're kind of breaking this into 2 diagonal pieces. One of them is going to be the error, and you're going to just do the, and you're going to include this as an additional error. You're not going to fit for the bias parameters, therefore, right?
But I'm going to use knowledge of these parameters that would
I know,
do
but-
the analysis by means of price, for example, to measure the theoretical.
I understand, but how can this be better than fitting for those nuisance parameters with the exact same assumption that you have made for their covariance and their correlations? How can this be better than the other one? It will be more conservative, but therefore will be potentially worse in terms of the fits. If you assume that those assumptions are good for your error matrix there, right? But so what is the claim here? Is that it's safer to do this? Because it's for sure,
No. I claim.
we're gonna give you worse results, but the claim is that it's going to be less biased, is that it?
I claimed in the beginning that this is an approach of practical relevance. So the point is, we can go to 4 bias parameters per redshift B, but this increases the dimension of the parameter space. And this will give better results, more accurate results. If we can avoid, for example, problems of volume projection, that's okay. But there is, even in the TS, the choice of restricting the analysis to B1. Exactly because we don't want that complexity, we don't find it worthwhile. So what to do is not a comparison with the first case, but with the second case, in which we restrict the analysis to B1. So is it better to use linear bias with a scale cut or use linear bias with theoretical error? This is the comparison. We're not trying to compete with the inclusion of more bias parameters.
Sorry. So not including bias parameters as parameters that you're gonna,
As
including your multi-column is going to be, so including those bias parameters and making the global fit is going to give you worse constraints than doing a larger covariance, that is increasing the covariance matrix. What is the exact claim here?
So the situation is like this. You can have full bias.
Yeah.
Plus scale cuts at 0.3 megapascal, more or less. This is one level of precision. The other is linear bias. Scale cuts at 0.1 H megapascal. This is a lower level precision, which is more practical.
Okay.
This has the practical inconvenience of determining Kmax. So we will consider this method promising if it gives the same results as the linear bias with the scale cut without the need of specifying Kmax, because it's automatically handled by the model.
So my question is, what happens? You have linear bias, scale cut with the increased covariance, but at 0.3, does it make your constraints better or worse than having full bias?
Okay, but then the comparison is with, then we have to estimate the error in this model itself.
Yeah, right.
Good. This is the method can be extended almost indefinitely. If we have a prediction that we can confront with data, we can calculate theoretical error by the same analysis. And then we have a model with B1, B2, BS square, and information on theoretical error of this model to include it here. Anyway, this is, I believe it can be done not with the same data, because this gives a fit. This is a fit assuming the bias model at second order works. So it only gives the error from here to here. But if we have knowledge of the residual of this fit, then we can do what you just proposed. We calculate the error here, and then we use this model. And we can have the benefit of not specifying Kmax here. So to summarize, we have constructed this modified likelihood with these covariance features. So how do we test it? We have two data sets. One is simulated. We just choose knowledge of bias parameters to construct the enclosed vector. And the other is data vectors that are issued from simulations. So it's the abacus and body simulation supplemented in the desk bias challenge to create galaxy centers. So we want to evaluate this model according to this criteria. So can it recover unbiased cosmology? Is it better than the scale cut in terms of precision? If we vary the data vector, does everything break? Is it robust if we change the fiducial cosmology? And is Kmax relevant or not? So these are the simulated data vectors. We have 3 levels of bias. So this is the possible range that we deduce from observations, and we try 3 data vectors that are at different levels of nonlinear bias. And for simulated, for vectors issued from simulations, we use the desk bias challenge data vectors, which are accurate up to 1H. So we can use it to test the independence of Kmax. So what we get is that, similar to other trials of this method, it is sensitive to these 3 moving parts: the envelope, the coherence length, and the mean error. So we can have, with a good choice of the envelope and of coherence length, we can get a result like this. If we don't make the optimal choice, we still get a result that is comparable with the scale cut, but whether it's going to be more precise or not depends on the choice. But in any case, we have Kmax in the case. And we have tested that this is robust and variations of the data vector. So this is one test of robustness. With this envelope, as I said, it's a conservative choice of the uncertainty. If we change the data factor, the strength of nonlinear bias, then nothing breaks. We still recover bias cosmology. Here, if we use very strong bias, then we start to see deviations. But it's not new to this method. It also happens with the scale cut. The Kmax is calibrated to 1 point. If we use a different data factor, then the Kmax may not be accurate. So this is now the test with vectors from simulations. with a certain choice of envelope, we see the improvement in precision. In every case, we see that Kmax is independent. Kmax is irrelevant. In all cases, we see results that are comparable, but whether the method delivers results better than the still depends on the choice of these moving parts.
Sorry, Abdias, can you explain again a little bit the difference between the theoretical error at Kmax one? The other one is a scale cut,
Okay.
higher K?
Okay, so you saw the error in the linked error.
Yes.
A scale cut is performed at 0.1H,
Right.
and the analysis with T is pushed to much smaller scales. But we still need to get
But you
to
have
define some Kmax, right?
you have a Kmax of one, isn't it?
Yes,
Right.
there is a number limit of the scales that are available, so I need to choose some Kmax
I see.
to perform the analysis. So the point is, we consider the analysis Kmax independent if we use a very large Kmax that you never have used in practice, and you don't get bias cosmology.
I see.
So this means that if you use 0.5, it works as well, because you tested a very extreme case. So this is the calculation. This is the modified likelihood. The uncertainty comes from these higher order terms in the bias expression. So there are three elements in the model. The covariance matrix, first we assume the error is Gaussian. So we have the diagonal of the matrix, coherence length, and the mean error. We tested it with likelihood analysis. So first, let me start with the unfavorable parts of this method. As we saw, in most cases, we get results that are comparable with the scale. So in previous studies, this has been called a success. But if we insist on improvement on precision, then we see an inconvenient sensitivity of the method with some choices that are made in the model. So which envelope we use and what coherence length we use, especially. We have made the choice of Gaussian probability. But this wasn't enough because we still have three elements in the modeling that have some ambiguous definitions. And that's to be expected because we're trying to model a random variable without access to full data. So we can't, as I said, measure the covariance matrix itself from the simulations. We can be informed by the simulations, but we have to make other guesses. So the method has, the scale cut has one moving part, which is the Kmax. This method has three. And the results are sensitive to it. Even if we still get independence from Kmax and results are comparable with the scale cut.
So can you give thought somehow, like the change independently, not having as the free variable, let's say Kmax, but the envelope and the dial equivalent in the case in like if you have the envelope being very like the theoretical error being very, very, very tight at all scales, and then pop up to super high errors at certain scale, would be that somehow equivalent to just imposing a hard Kmax cut?
Yes.
So I guess that, I mean, somehow it's very nice that it's agnostic to not specifying Kmax, but somehow that dependency it's encoded in the terms of the envelope shape, no?
If we restrict the envelope to this shape, this is the envelope, and here infinite.
Yeah.
That's equivalent to a scale cut.
So
But that may not be the optimal choice.
yeah, so it's like
Because when we consider data, which is something that's smooth.
And the fact, I guess that the thing is that the way in which you calibrate the different kinds of envelopes that you are available are based on some set of simulations where you
Yes.
measure the coevolution relations in between bias parameters.
Well, the envelope, as we said, is the element besides the mean error, is the element that is informed by simulations. But in the absence of correlations, bias parameters, we can't say it is exactly measured by this data. So there is some room for further instance. This is why we test one conservative choice, which is double the standard deviation that we get from this data. So what are the favorables? Most of the results are comparable with the scale cut without any dependence on the choice of K-max. If we do it correctly, we get a gain in precision. And this is robust under variations of the data range. So what we suggest to improve this approach is try to get more reliable, more details on the distributions of bias parameters. I think Nicholas Mulron, which is one of the collaborators, has been working on correlations between bias parameters from simulations. This is good. This could improve the calibration of the envelope, so it would reduce the freedom that we have in the model. And the second suggestion is the one that I would propose. We could use full bias, measure the residual fit with simulations, and then we include this theoretical error information in the analysis so we can dispense with the choice of K-max, possibly with the gain precision. So this is all. Thank you.
So Abdias, do you think at some point maybe try to see the impacts of going beyond Gaussian likelihoods? Because since you are going now to higher order bias terms, it's going like
Of the data or theoretical?
of, oh, I don't know. Because a Gaussian likelihood is under the assumption that the distributions are Gaussian, right?
Yeah.
Like you're going to higher
Define
order.
likelihood is Gaussian if, sorry.
If you're going to higher order perturbations, then you will have like more non-Gaussian terms, and it really depends on these galaxy bias, right?
Yes, that's true. Well, as I said, after we make the assumption of Gaussianity in the error, there's still many things that are ambiguous.
Right.
So I don't see at this level what is the advantage of considering all the shapes of the
Right.
of theoretical error.
Right.
Well, there is an advantage in considering non-Gaussianities in the likelihood of the data.
Yes.
That's something we know for certain that improves the analysis.
Okay.
But then the resulting formula is not so simple. It's not covariance total being data plus error. Because this assumes this is Gaussian.
Yeah.
But then we can do it numerically.
Right.
We can marginalize of the error numerically.
So I'm not sure about this because like some people on the group that I was, they work on this Lagrangian bias expansion. And I guess that this is like Eulerian bias expansion. And I think that there's not a one-to-one mapping in between what those parameters actually are.
At a certain order, it's
But the thing is that the scale cuts are different depending on what perturbation theory you are using. So I had just I wanted to know a little bit how this, like if something like this could be done at that level and how would the scale cuts compare or.
well, you can, it's just a matter of in the envelope, as I said, which is informed by the simulations, we can get, if we get results in Lagrangian bias and we are using second order, then we use the transformations to Eulerian bias at the same order. And we measure mean values and variances, and we use the same data to model the envelope. So it's not an issue. And this paper from the Best Bias Challenge, they tested both approaches, Eulerian and Lagrangian, and they saw this K-max is appropriate for both. So it doesn't seem to affect the regime of validity of the fields.
Yes, we. Okay, we resume at 11:30. The next topic.
What's the coffee downstairs, you know?
Yeah, there is a machine you can do.